Example, solve y double prime minus 2y prime minus 3y equals t squared using variation of parameters. Before I start, I want to note that if given the choice, I probably wouldn't use variation of parameters to solve this differential equation. The non-homogeneous term is t squared, and that's a polynomial. Anytime my non-homogeneous term is a combination of polynomial, exponential, and or sinusoidal functions, I prefer to use the method of undetermined coefficients. However, the purpose of this example is to illustrate how to use a shortcut for variation of parameters, so that's what I'm going to use. To start solving any differential equation using variation of parameters, we need to find the complementary solution. The complementary equation for this example is y double prime minus 2y prime minus 3y equals 0. So the characteristic equation is r squared minus 2r minus 3 equals 0. Factoring the left side, I get r minus 3 times r plus 1 equals 0. So the roots are r equals 3 and r equals negative 1. And the complementary solution is yc equals c1 e to the 3t plus c2 e to the negative t. Now, to use variation of parameters, we say that the particular solution will have the form yp equals v1 y1 plus v2 y2, where y1 and y2 are the fundamental solutions from the complementary solution. In this case, since yc equals c1 e to the 3t plus c2 e to the negative t, y1 equals e to the 3t, and y2 equals e to the negative t. The long way to do variation of parameters would be to now find formulas for the first and second derivatives, plug them into the original differential equation, and then find v1 and v2. This process involves solving a system of equations. The shortcut is to jump straight to the system of equations because it always ends up being the following two equations: v1 prime y1 plus v2 prime y2 equals 0, and v1 prime y1 prime plus v2 prime y2 prime equals f of t, where f of t is the non-homogeneous term divided by the coefficient on y double prime. Since the coefficient on y double prime in our differential equation is just a 1, f of t is just the non-homogeneous term t squared. y1 prime equals 3e to the 3t, and y2 prime equals negative e to the negative t. So our system of equations is v1 prime e to the 3t plus v2 prime e to the negative t equals 0, and v1 prime times 3e to the 3t plus v2 prime times negative e to the negative t equals t squared. Now, we solve the system to find v1 prime and v2 prime however we choose. Personally, I like to use Cramer's rule, so the first thing I do is write this as a matrix equation. The 2 by 2 matrix, e to the 3t, e to the negative t, 3e to the 3t, negative e to the negative t, times the column vector v1 prime, v2 prime, equals the column vector 0 t squared. The coefficient matrix A is the 2 by 2 matrix e to the 3t, e to the negative t, 3e to the 3t, negative e to the negative t, and its determinant is e to the 3t times negative e to the negative t minus e to the negative t times 3e to the 3t, which equals negative e to the 2t minus 3e to the 2t, which equals negative 4e to the 2t. A1, the matrix that we get from replacing the first column of A with the column vector 0t squared, equals 0 e to the negative t, t squared, negative e to the negative t, and its determinant is equal to 0 times negative e to the negative t minus e to the negative t times t squared, which equals negative t squared e to the negative t. A2, the matrix we get from replacing the second column of A with the column vector 0t squared, is e to the 3t, 0, 3e to the 3t, t squared, and its determinant is e to the 3t times t squared minus 0 times 3e to the 3t, which equals t squared e to the 3t. Kramer's rule says that v1 prime is equal to the determinant of a1 divided by the determinant of a, which equals negative t squared e to the negative t divided by negative 4e to the 2t, which equals 1/4 t squared e to the negative 3t. And v2 prime equals the determinant of a2 divided by the determinant of a, which equals t squared e to the 3t divided by negative 4e to the 2t, which equals negative 1/4 t squared e to the t. Since these are formulas for the derivatives of v1 and v2, we have to integrate with respect to t. v1 equals the integral of 1/4 t squared e to the negative 3t dt, and v2 equals the integral of negative 1/4 t squared e to the t dt. Both integrals will require using integration by parts twice. To avoid confusion with variables, I'm going to use the letters u and s instead of the usual u and v, and say that the integral of u ds is equal to u times s minus the integral of s du. For both integrals, I'd use t squared for u and the exponential function for ds. For the first integral, u equals t squared, so du equals 2t dt, ds equals e to the negative 3 dt, so s equals negative 1/3 e to the negative 3t. So I get 1/4, open parentheses, negative 1/3 t squared e to the negative 3t minus the integral of negative 1/3 e to the negative 3t times 2t dt, which equals negative 1/12 t squared e to the negative 3t plus 1/6 of the integral of t e to the negative 3t dt. I now need to use integration by parts again, so I'll use u equals t and ds equals e to the negative 3t dt. That means du equals dt and s equals negative 1/3 e to the negative 3t. So I get negative 1/12 t squared e to the negative 3t plus 1/6 times open parentheses negative 1/3 t e to the negative 3t minus the integral of negative 1/3 e to the negative 3t dt, which equals negative 1/12 t squared e to the negative 3t minus 1/18 t e to the negative 3t minus 1/6 times open parentheses 1/9 e to the negative 3t, which equals negative 1/12 t squared e to the negative 3t minus 1/18 t e to the negative 3t minus 1/54 e to the negative 3t. I'll leave it to you to go through a similar process to find V2. You should get V2 equals negative 1/4 t squared e to the t plus 1/2 t e to the t minus 1/2 e to the t. Note that I'm not including integration constants because I don't need to, because the arbitrary constants are already accounted for by the complementary solution, which I will add on at the very end. I am just trying to find a particular solution right now, so I don't need to worry about the arbitrary constants. Once we have V1 and V2, we plug them back into our formula for the particular solution. Yp equals V1 y1 plus V2 y2, which equals V1 e to the 3t plus V2 e to the negative t. So Yp equals open parentheses negative 1/12 t squared e to the negative 3t minus 1/18 t e to the negative 3t minus 1/54 e to the negative 3t, close parentheses e to the 3t plus open parentheses negative 1/4 t squared e to the t plus 1/2 t e to the t minus 1/2 e to the t, close parentheses, times e to the negative t. Now I can clean this up quite a bit by distributing the exponential functions through and combining like terms. The exponentials are going to completely cancel out because every term in the first set of parentheses has an e to the negative 3t in it, and e to the negative 3t times e to the 3t equals 1. Similarly, every term in the second set of parentheses has e to the t, which will be multiplied by e to the negative t, resulting in 1. So Yp equals negative 1/12 t squared minus 1/18 t minus 1/54 minus 1/4 t squared plus 1/2 t minus 1/2. So Yp equals open parentheses negative 1/12 minus 1/4 close parentheses t squared plus open parentheses 1/2 minus 1/18 close parentheses t minus 1/2 minus 1/54, which simplifies to Yp equals negative 1/3 t squared plus 4/9 t minus 14/27. The final step is to create the general solution by adding the particular solution and the complementary solution together. So y equals negative 1/3 t squared plus 4/9 t minus 14/27 plus c1 e to the 3t plus c2 e to the negative t. So you'll see that this faster method still leaves a lot of work to be done. You still have to use algebra to solve for v1 prime and v2 prime. Whether that's Cramer's rule or another method is up to you. And you still have to go through the process of integrating to find v1 and v2. Even if you use formulas for variation of parameters, which can eliminate the system solving portion of the problem, you still have to do the integration at the end. And in most cases, that's where the bulk of the work of the problem is anyway. All of the methods for speeding up this process rely on the fact that the system and the solution to the system always works out the same way.